Okay, now we are going to learn to find the absolute extremum for a closed bounded region R, and this could be looking for absolute maximum or absolute minimum or both of them. Okay, now to find the absolute, well, let's say we are looking for many of them. Okay, so to find the absolute extremum or absolute extrema, okay, what we need to do is to list the interior points of R, or we say list the critical points of R where F have extrema and evaluate the F. Next, we just need to list the boundary points of R where F have extrema, and again we need to evaluate the F. Lastly, we compare all the points that we found from step 1 and step 2, and then we look for the maximum from all the F here and the minimum from all the F here, and we decide what is the absolute maximum and absolute minimum on this closed bounded region R. Now, for example, let's say we want to find the absolute extreme values of F, which is equals to 2 plus 2x plus 2y minus x squared minus y squared. On a triangular region in the first quadrant bounded by the lines x equals to 0, y equals to 0, and y equals to 9 minus x. So, it is always a good practice if we are able to visualize the graph of f. By taking z equals to f, and we complete the squares for this function, we get z equals to negative of x minus 1 squared plus y minus 1 squared plus 4. Which this equation gives a circular paraboloid that opens towards the negative side of z-axis with vertex at 1, 1, 4. Now in the graph, this is how the paraboloid looks like, okay, the circular paraboloid, and we would like to find the absolute extrema on this paraboloid, which is bounded by the x equals to 0, which is this blue plane, okay, as you can see from here. Okay, here is one of the boundary, and then y equals to 0. This is another boundary, okay, and also y equals to 9 minus x, which you can see from here, it is far at this end, so we have to zoom out so that you can see the intersection. Well, let's see. Yep, it intersects, and let's turn, okay, make it more obvious. Yes, you see this part? Okay, so here is the intersection. So sometimes if we want to draw it according to scale, it's rather hard to see. You see that? This is the region, triangular region, which is so small after we zoom out. So let's look at this triangular region on a two-dimensional, on the xy plane. So this is the graph of the triangular region that is bound by this x-axis, y equals to 0, y-axis, that is x equals to 0, and the line y equals to 9 minus x. Okay, so after getting the region, then we start to go to look for the critical points. Okay, you can see from here, to find the critical point, well, we have to go through the first derivative test, that is to find fx, fy, okay, which is 2 minus 2x for fx, and 2 minus 2y for fy. And then we equalize them to 0, which we will get x equals to 1 and y equals to 1. And then getting this critical point, we need to be sure the point that we get here is either maximum or minimum. Then we do the second derivative test, that is to find fxx, which is negative 2, fyy, which is negative 2 as well, and fxy, which is equals to 0. Then we look for the discriminant, which is fxx by fyy minus the square of fxy, that will give us 4. When it is 4, which means it is positive, that means the point 1, 1, it is an interior extreme point, it means it is either maximum or minimum. Then we'll just put a dot at the graph, okay, indicate that this is one of the points that we have to consider. Next, now since this is a triangular region, this region have vertices. So we have to list down all the vertices, which is 0, 0, here, 9, 0, this point, and 0, 9, and this point. Okay, we have to consider all these points to find the maximum and minimum. Okay, lastly, we want to consider the borders. Okay, here we have 3 sides, so we have to find out one by one. Let's take a look at the first one. The first side is x equals 0. X equals 0 is this line. At this line, we'll substitute x equals 0 into this function, into the x, then we will have 2 plus 2y minus y squared. And then from here, after we simplify the function, okay, we look for the derivative of this function, that is 2 minus 2y, and we equalize it to 0. And this one will lead us to y equals to 1. So we have one critical point at 0, 1, which is over here. Okay, and then the second side, which is y equals 0, we'll take a look here. At y equals 0, we just need to substitute 0 into the y here, and we get a function in terms of x only, which is 2 plus 2x minus x squared. So when it is a function of one variable only, when we want to find the critical point, we just need to differentiate with respect to x, and we get 2 minus 2x, and equalize it to 0, we get x equals to 1. And this gives us another point that is 1, 0, which is over here. Lastly, we need to find a critical point at this side. So at this side, we have y equals to 9 minus x. Okay, so we substitute y equals to 9 minus x into the function here, the y here, and we get a function in terms of x only. Okay, we substitute, we expand, we simplify, and we get fx equals to negative 2x squared plus 18x minus 61. And by differentiating the f with respect to x, we get negative 4x plus 18, and then we equalize the function, we equalize the derivative to 0, we get x equals to 9 over 2. After we get x equals to 9 over 2, we need to substitute back this 9 over 2 into the x here in order for us to get the y. Okay, and after getting the y, we will get the point 9 over 2, 9 over 2. Remember, your x is supposed to be substituted inside here and not here. And then, let's take a look at the points that we have found. So the interior point is 1, 1, okay, 1 point. And the vertices, we have 3 points, okay. And then the other boundary extreme points, we have another 3 points. So altogether, we have 7 points. And substitute the points into the function, we get all these values, okay. And then by comparing all this value, we find that 4 is the maximum value, okay, and negative 61 is the minimum value, which occur at 2 points here. So we can look at the graph again. Here is the graph, okay. Let's take a look here. So if I keep on zooming out, we see that at this side, which is at this plane, okay, we have the minimum of negative 61 at 2 points. These 2 points happen at the vertices here, and then the maximum it's 4. Okay, the maximum, well, let me move the graph. Oops. Here, this is the maximum at 4, and then this 4, it is at, well, let's see here. This is the scale of 2, so you see this white dot, it is at 1, 1. So come back here. So we can say the conclusion. We can write here the maximum is 4 at 1, 1, and the minimum is negative 61 at 0, 9, and 9, 0. Sometimes you can just write like this, or if you prefer, you can write the absolute maximum and the absolute minimum instead of just writing the maximum and minimum. So this is the summary. Look back at the summary. To find the absolute extremum, what we need to do is to list the interior points of R, list the boundary of R where f have extrema, and then we evaluate the f, and lastly we compare and find the absolute extrema.